ਇਸ ਤਰ੍ਹਾਂ ਦੇ ਗੋਲਾਕਾਰ ਰਿੰਗਸ ਵਰਗੇ ਪੈਟਰਨਸ ਸੂਰਜ, ਚੰਨ ਅਤੇ ਹੋਰ ਖਗੋਲੀ ਵਸਤਾਂ ਦੁਆਰਾ ਬਣਦੇ ਨਜ਼ਰ ਆਉਂਦੇ ਹਨ। ਇਹ ਪੈਟਰਨਸ ਲਾਈਟ ਤੇ ਡਿਫਰੈਕਸ਼ਨ ਕਾਰਨ ਬਣਦੇ ਹਨ। ਥਿਨ ਕਲਾਉਡਸ ਦੇ ਦੁਆਲੇ ਸਿਲਵਰ ਲਾਈਨਿੰਗ ਸੂਰਜੀ ਪ੍ਰਕਾਸ਼ ਜਾਂ ਸਨਲਾਈਟ ਤੇ ਡਿਫਰੈਕਸ਼ਨ ਦਾ ਇੱਕ ਬੜਾ ਹੀ ਸੋਹਣਾ ਉਦਾਹਰਣ ਹਨ। ਅੱਜ ਦੇ ਪਾਠ ਵਿੱਚ ਤੁਹਾਨੂੰ ਦੱਸਾਂਗੇ ਕਿ ਡਿਫਰੈਕਸ਼ਨ ਕੀ ਹੁੰਦਾ ਹੈ।
Dear students, ਅੱਜ Diffraction and Polarization ਦੀ ਇਸ ਕਲਾਸ ਵਿੱਚ ਤੁਹਾਡਾ ਸਾਰਿਆਂ ਦਾ ਸਵਾਗਤ ਹੈ। Diffraction ਅਤੇ Polarization ਮਾਈਕਰੋਸਕੋਪਿਕ ਫਿਨੋਮੇਨਾ ਹਨ ਜਿਨ੍ਹਾਂ ਨੂੰ ਅੱਜ ਅਸੀਂ ਵਿਸਥਾਰ ਨਾਲ ਜਾਣਾਂਗੇ। ਸ਼ੁਰੂਆਤ ਤੋਂ ਪਹਿਲਾਂ ਆਓ ਅੱਜ ਦੇ ਲਰਨਿੰਗ ਆਬਜੈਕਟਿਵਸ ਵੀ ਜਾਣ ਲਈਏ।
After the completion of this chapter, the students will be able to describe Fraunhofer diffraction, describe the diffraction pattern and obtain an equation for the path difference, discuss the differences between the diffraction and the interference, describe the polarization of light wave, demonstrate the transverse nature of light waves, state the Malus law and Brewsters law.
ਪਿਛਲੀ ਕਲਾਸ ਵਿੱਚ ਅਸੀਂ ਜਾਣਿਆ ਸੀ ਕਿ ਕਿਸੇ ਦੋ ਕੋਹੈਰੈਂਟ ਸੋਰਸਸ ਤੋਂ ਨਿਕਲੀਆਂ ਵੇਵਸ ਦੇ ਸੁਪਰਪੋਜੀਸ਼ਨ ਕਾਰਨ ਇੰਟਰਫੇਰੈਂਸ ਹੁੰਦੀ ਹੈ। ਅੱਜ ਡਿਫਰੈਕਸ਼ਨ ਬਾਰੇ ਪੜਾਂਗੇ। ਆਮ ਤੌਰ ਤੇ ਅਸੀਂ ਇਹੀ ਜਾਣਦੇ ਹਾਂ ਕਿ ਲਾਈਟ ਸਿੱਧੀ ਰੇਖਾ ਵਿੱਚ ਹੀ ਚੱਲਦੀ ਹੈ, ਪਰ ਜਦੋਂ ਇਹ ਕਿਸੇ ਬੈਰੀਅਰ ਉੱਤੋਂ ਲੰਘਦੀ ਹੈ ਤਾਂ ਇਸ ਦੀ ਟੈਂਡੈਂਸੀ ਬੈਂਡ ਹੋ ਕੇ ਸਪਰੈਡ ਆਊਟ ਹੋਣ ਦੀ ਹੋ ਜਾਂਦੀ ਹੈ। In fact, if light waves pass over an obstacle or pass through a narrow opening, they bend partially at the edges of the obstacle or the opening. This spreading of light waves that pass through a narrow opening or move past an obstacle is called diffraction. Breaking up of light into different directions is referred as diffraction. Commonly, when light from a point source passes through a small circular aperture, it should produce a bright dot as an image. But it produces a diffused circular disk surrounded by much fainter concentric circular rings. This is an important example of diffraction because the eye and many optical instruments have circular apertures. However, this smearing of the image of the point source can be controlled with aperture size. If the opening or the obstacle is large as compared to the wavelength of the light, the bending of light waves is not noticeable. But if the size of the obstacle or opening is comparable to the wavelength of light, the diffraction is quite prominent. ਜਦੋਂ ਲਾਈਟ ਵੇਵਸ ਕਿਸੇ ਬਹੁਤ ਹੀ ਨੈਰੋ ਓਪਨਿੰਗ ਵਿੱਚੋਂ ਪਾਸ ਕਰਦੀਆਂ ਹਨ ਤਾਂ ਉਹ ਉਸ ਓਪਨਿੰਗ ਦੇ ਐਜਸ ਤੋਂ ਪਾਰਸ਼ਲੀ ਬੈਂਡ ਹੋ ਜਾਂਦੀਆਂ ਹਨ। ਇਸ ਬੈਂਡਿੰਗ ਵਜੋਂ ਲਾਈਟ ਆਬਸਟੈਕਲ ਦੀ ਜਿਓਮੈਟ੍ਰੀਕਲ ਸ਼ੈਡੋ ਵਿੱਚ ਪੈਨੀਟ੍ਰੇਟ ਕਰ ਜਾਂਦੀ ਹੈ। ਇਸ ਤਰ੍ਹਾਂ ਲਾਈਟ ਆਪਣੇ ਲੀਨੀਅਰ ਪਾਥ ਤੋਂ ਡੇਵੀਏਟ ਹੋ ਕੇ ਉੱਥੇ ਪਹੁੰਚ ਜਾਂਦੀ ਹੈ ਜਿੱਥੇ ਸ਼ੈਡੋ ਬਣਨੀ ਚਾਹੀਦੀ ਸੀ। ਕਿਸੇ ਨੈਰੋ ਓਪਨਿੰਗ ਵਿੱਚੋਂ ਪਾਸ ਕਰਨ ਤੋਂ ਬਾਅਦ ਲਾਈਟ ਵੇਵਸ ਦਾ ਬੈਂਡ ਹੋਣਾ ਹੀ ਡਿਫਰੈਕਸ਼ਨ ਕਹਾਉਂਦਾ ਹੈ। In general, diffraction of light is of two types: Fresnel diffraction and Fraunhofer diffraction. According to Fresnel, diffraction occurs when the source of light is at a finite distance from the slit. On the other hand, according to Fraunhofer, diffraction occurs when a plane wavefront is incident on a slit and the wavefront emerging from the slit is also a plane wavefront. Here, it should be noticed that both the source and the screen are at finite distances from the slit.
You are observing a plane wavefront advancing towards a narrow opening. When the wavefront reaches the opening, its major part is blocked and only a small part passes through the opening. According to Huygens' principle, each unblocked point on the wavefront acts as a source of secondary wavelets. As a result of superposition of secondary wavelets, bending of wave occurs from the portion of the wavefront that is allowed to pass. Since the opening is small, the waves spread more after passing through the opening. Dark and bright fringes are obtained on the screen.
ਯੰਗਸ ਐਕਸਪੈਰੀਮੈਂਟ ਵਿੱਚ ਅਸੀਂ ਕਿਹਾ ਸੀ ਕਿ ਇੱਕ ਸਿੰਗਲ ਨੈਰੋ ਸਲਿਟ ਇੱਕ ਨਵੇਂ ਸੋਰਸ ਦਾ ਕੰਮ ਕਰਦੀ ਹੈ ਜਿੱਥੋਂ ਲਾਈਟ ਸਪਰੈਡ ਆਊਟ ਹੁੰਦੀ ਹੈ। ਯੰਗ ਤੋਂ ਪਹਿਲਾਂ ਵੀ ਕੁਝ ਐਕਸਪੈਰੀਮੈਂਟਰਸ ਜਿਵੇਂ ਕਿ ਨਿਊਟਨ ਨੇ ਹੋਲਸ ਅਤੇ ਸਲਿਟਸ ਤੋਂ ਲਾਈਟ ਸਪਰੈਡ ਹੁੰਦੀ ਨੋਟਿਸ ਕੀਤੀ ਸੀ। ਇਹ ਨੁਕਰਾਂ ਤੋਂ ਮੁੜਦੀ ਨਜ਼ਰ ਆਉਂਦੀ ਹੈ। ਅਜਿਹੇ ਇਫੈਕਟਸ ਡਿਫਰੈਕਸ਼ਨ ਕਹਾਉਂਦੇ ਹਨ। ਇਹ ਵੇਵ ਥਿਉਰੀ ਦੇ ਆਧਾਰ ਤੇ ਚੰਗੀ ਤਰ੍ਹਾਂ ਸਮਝਿਆ ਜਾ ਸਕਦਾ ਹੈ। ਜੇ ਯੰਗਸ ਐਕਸਪੈਰੀਮੈਂਟ ਵਿੱਚ ਡਬਲ ਸਲਿਟ ਨੂੰ ਕਿਸੇ ਸਿੰਗਲ ਨੈਰੋ ਸਲਿਟ ਨਾਲ ਰਿਪਲੇਸ ਕਰ ਦਿੱਤਾ ਜਾਵੇ ਅਤੇ ਮੋਨੋਕ੍ਰੋਮੈਟਿਕ ਸੋਰਸ ਨਾਲ ਇਲੂਮੀਨੇਟ ਕਰ ਦਿੱਤਾ ਜਾਵੇ ਤਾਂ ਇੱਕ ਸੈਂਟਰਲ ਬ੍ਰਾਈਟ ਰੀਜਨ ਵਾਲਾ ਚੌੜਾ ਜਿਹਾ ਪੈਟਰਨ ਨਜ਼ਰ ਆਉਂਦਾ ਹੈ। ਇਸ ਦੀਆਂ ਦੋਨੋਂ ਸਾਈਡਾਂ ਤੇ ਆਲਟਰਨੇਟ ਡਾਰਕ ਅਤੇ ਬ੍ਰਾਈਟ ਰੀਜਨਸ ਹੁੰਦੇ ਹਨ ਜਿਨ੍ਹਾਂ ਦੀ ਇੰਟੈਂਸਿਟੀ ਬਾਹਰ ਵੱਲ ਨੂੰ ਘਟਦੀ ਜਾਂਦੀ ਹੈ। Calculations show that intensity at the first secondary maximum is less than 5% of the intensity of the middle of the central maximum. This shows that most of the light incident on the slit is diffracted into the central maximum.
Let a source of monochromatic light be held at a small distance from a slit. Let B be the width of the slit, D the distance of the screen from the slit, and lambda the wavelength of the monochromatic light. Consider a plane wavefront incident on a slit AB which is blocked except between points A and B. According to Huygens' principle, each point on wavefront AB sends out secondary wavelets in all directions. The diffraction pattern on the screen is formed due to the superposition of these secondary wavelets. To obtain the central maximum, all the points on the wavefront between A and B are in phase. The wavelets which fall on the convex lens parallel to its principal axis meet at point O in the same phase. Since these waves are in phase with each other as they leave AB and their path difference is 0, all the waves arrive in phase at point O and give rise to central maximum or central bright fringe at O. To obtain the positions of secondary minima, we consider point P on the screen. Let the rays reaching point P make an angle theta with the principal axis of the lens CO. It is clear that the wavelets from different parts of the slit do not reach at point P in phase. Initially, these are in same phase. Rays from point A and B will have a path difference equal to Bn. From right angle ANB, Bn is equal to AB sin theta. That is, rays from point A and B will have a path difference equal to B sin theta. If this path difference is equal to the wavelength of light, then point P will have minimum intensity, or the point P would become the first secondary minimum. The location of the first secondary minimum is given as lambda equal to B sin theta. This is the first condition of destructive interference. Now, point P on the screen will be the position of first secondary minimum. The reason for first secondary minimum at point P is that the ray from the top of the slit travels exactly one wavelength more than the ray from the bottom edge. But the ray passing through the center C of the slit travels a distance lambda by 2 more than the ray at the bottom edge. The rays from points A and C will have a path difference equal to b by 2 sine theta or lambda by 2. Therefore, the ray from the top of the slit is 180 degree out of phase with ray at the center of the slit, and so the two waves meet destructively at point P and produce the first secondary minimum. Similarly, ray from the bottom of the slit is 180 degree out of phase with the ray at the center of the slit, and so the two waves also meet destructively at point P and so on. Thus, each ray in the bottom half of the slit cancels out a corresponding ray in the upper half. Hence, the position of the first secondary minimum can be obtained from the expression lambda equal to b sine theta.
Similarly, the position of second secondary minimum can be obtained when this path difference is 2 lambda. Let the rays be travelling at an angle theta with CO such that the ray from the top of the slit travels exactly 2 wavelengths more than the ray from the bottom of the slit. The rays from the bottom quarter of the slit will cancel with those in the quarter just above it, because the path difference is lambda by 2. Also, the rays through the quarter of the slit just above the center C will cancel with those through the top quarter. Thus, the location of the second secondary minimum can be obtained from the expression 2 lambda equal to b sine theta. Similarly, we can obtain third secondary minimum when the path difference is 3 lambda. In general, for nth secondary minimum, path difference is equal to n lambda, where n is equal to 1 or 2 or 3 or so on. In this case, let the rays be travelling at an angle theta n with CO so that b sine theta n is equal to n lambda or sine theta n is equal to n lambda by b. You might have noticed that n is equal to 1 or 2 or 3 or so on, but not 0. Because if n is equal to 0, it will locate at point O, that is the central bright fringe. If yn is the distance of the nth minimum from the center O, then from the triangle COP, tan theta n is equal to OP upon CO or yn upon d. For small theta n, we get yn upon d is equal to n lambda upon b, or yn equal to n lambda d upon b. So now we can find out the width of secondary maximum as beta equal to yn minus 1, that is beta is equal to n lambda d upon b minus n minus 1 into lambda d upon b, which is equal to d lambda upon b. Since it is independent of n, hence secondary maxima are of same width. Similar to the secondary minima, we can also find the position of secondary maxima. between each pair of minima, there is a bright fringe, or in other words, a secondary maximum. We know that the brightest maximum occurs at the center point and the other secondary maxima get successively dimmer. Let us calculate the positions of these secondary maxima. If we consider the rays travelling at angle theta with the principal axis of the lens CO, such that the ray from the top of the slit travels a distance 3 lambda by 2 more than the ray from the bottom edge. In this case, the rays from the bottom third of the slit will cancel in pairs with those in the middle third, as they will be out of phase by lambda by 2. However, light from the top third of the slit will still reach the screen, so that there will be a bright spot, but not as bright as the central spot at O. Therefore, the location of the first secondary maximum can be obtained with path difference 3 lambda by 2 is equal to b sin theta. Similarly, the second secondary maximum is located on the screen when path difference is 5 lambda by 2, that is, when 5 lambda by 2 is equal to b sin theta. In general, for nth secondary maximum, the condition is b sin theta n equal to 2n plus 1 into lambda by 2, where n is equal to 1 or 2 or 3 or so on. If yn dash is the distance of the nth maximum from the center O, then tan theta n is equal to yn dash upon d. For small theta n, we get yn dash upon d equal to 2n plus 1 into lambda upon 2b, or yn dash is equal to 2n plus 1 into lambda into d upon 2b. Hence, the width of secondary minimum is beta dash equal to yn dash minus yn minus 1 dash, which is equal to 2n plus 1 into lambda d upon 2b minus 2 into n minus 1 plus 1 into lambda d upon 2b, which is equal to lambda d upon b. Since it is independent of n, hence secondary minima are also of same width. Let us find out the width of central maximum. The width of central maximum is the distance between first secondary minimum on either side of O. If P is the position of first secondary minimum and OP is equal to y1, then the width of the central maximum beta 0 is equal to 2y1, which is equal to 2d lambda by b. Since y1 is equal to lambda into d upon b, therefore beta 0 is equal to twice of lambda into d upon b.
It has been found that if intensity at center is I0, then the intensity at first secondary maximum is about I0 by 22, and at second secondary maximum it is I0 by 61, and so on.
Next important microscopic phenomenon is polarization. Before continuing our discussion on polarization, let me share the difference between interference and diffraction of light. Though both interference and diffraction are because of superposition of light waves, there are some important differences between them. Interference arises due to the superposition of waves from two coherent sources, whereas diffraction is produced as a result of waves coming from different parts of the same wavefront. In interference, all the bright fringes are of the same intensity. But in diffraction pattern, all bright fringes are not of the same intensity. In interference, the width of the fringes may or may not be the same. On the other hand, diffraction fringes are always of varying widths. In interference, the points of minimum intensity are perfectly dark. However, in diffraction pattern, the intensity at minima is never zero. Interference ਅਤੇ diffraction effects longitudinal ਤੇ transverse ਦੋਨਾਂ ਤਰ੍ਹਾਂ ਦੀਆਂ waves ਨਾਲ ਹੋ ਸਕਦੇ ਹਨ। ਹਾਂ, polarization ਸਿਰਫ transverse wave ਦੀ ਹੀ ਹੋ ਸਕਦੀ ਹੈ। Ordinary light ਲਈ ਇਸ ਦੇ propagation ਦੇ perpendicular plane ਵਿੱਚ electric vector ਦੀਆਂ vibrations ਹਰ possible direction ਵਿੱਚ symmetrical ਹੁੰਦੀਆਂ ਹਨ। ਜੇ ਕਿਸੇ ਤਰ੍ਹਾਂ electric vector ਦੀਆਂ vibrations ਨੂੰ ਲਾਈਟ ਦੇ propagation ਦੇ perpendicular plane ਵਿੱਚ ਕਿਸੇ single direction ਵਿੱਚ ਸੀਮਿਤ ਕੀਤਾ ਜਾ ਸਕੇ ਤਾਂ ਇਸ ਨੂੰ plain polarized light ਕਿਹਾ ਜਾਂਦਾ ਹੈ ਅਤੇ ਇਸ ਵਰਤਾਰੇ ਨੂੰ polarization ਕਹਿੰਦੇ ਹਨ। Let me now show you an activity to give you an understanding of polarization.
When a rope is shaken up and down, the wave produced is plane polarized as the rope vibrates in a single vertical plane. We say that the wave is vertically plane polarized. Similarly, when the rope is shaken side to side, the wave produced is again plane polarized since the rope vibrates only in horizontal plane. We say that the wave is horizontally plane polarized. Such a wave can pass through a horizontal slit but not through a vertical slit. If we take two slits parallel to each other, the wave can pass through parallel slits but cannot travel through perpendicular slits. Here, second slit stops all vertical components of the wave.
Most of the sources of light emit unpolarized light as their vibrations take place in randomly oriented directions perpendicular to the travel of the wave. The reason is simple. We know that light is emitted by a source because of electron transitions within the individual atoms of the source. These transitions occur rapidly and each gives rise to a wave for a short time. Thus, the resultant light consists of many different waves originating at random times from atoms that are oriented randomly relative to each other. However, the amplitudes of vibrations are equal.
Unpolarized light ਕਈ ਸਾਰੀਆਂ waves ਦੀ ਬਣੀ ਹੁੰਦੀ ਹੈ ਜਿਹੜੀਆਂ ਇੱਕ ਦੂਜੇ ਨਾਲ randomly oriented ਹੁੰਦੀਆਂ ਹਨ। ਜਿਸ ਤਰ੍ਹਾਂ ਇੱਕ ਰੱਸੀ ਦੁਆਰਾ ਬਣੀਆਂ waves ਇੱਕ ਸਲਿਟ ਤੋਂ polarize ਹੁੰਦੀਆਂ ਹਨ, ਠੀਕ ਉਸੇ ਤਰ੍ਹਾਂ unpolarized light ਵੀ polarize ਕੀਤੀ ਜਾ ਸਕਦੀ ਹੈ। ਇੱਕ ਸਿੰਗਲ ਸਲਿਟ ਦੀ ਜਗ੍ਹਾ ਅਜਿਹਾ ਮਟੀਰੀਅਲ ਵਰਤਿਆ ਜਾਂਦਾ ਹੈ ਜਿਹੜਾ ਕਈ ਸਾਰੀਆਂ ਸਲਿਟਸ ਦਾ ਇਫੈਕਟ ਦਿੰਦਾ ਹੈ। ਸਭ ਤੋਂ ਜ਼ਿਆਦਾ ਕਾਮਨ ਪੋਲਰਾਈਜ਼ਿੰਗ ਮਟੀਰੀਅਲ ਪੋਲਰੋਇਡ ਕਹਾਉਂਦਾ ਹੈ। ਹਰ ਪੋਲਰੋਇਡ ਦਾ ਇੱਕ ਖਾਸ ਕੈਰੈਕਟਰਿਸਟਿਕ ਡਾਇਰੈਕਸ਼ਨ ਹੁੰਦਾ ਹੈ ਜਿਹੜਾ ਟਰਾਂਸਮਿਸ਼ਨ ਐਕਸਿਸ ਕਹਾਉਂਦਾ ਹੈ। ਇਲੈਕਟ੍ਰਿਕ ਵੈਕਟਰ ਜਿਸ ਤੇ ਵਾਈਬ੍ਰੇਟ ਕਰਨ ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਟਰਾਂਸਮਿਸ਼ਨ ਐਕਸਿਸ ਤੇ ਪੈਰਲਲ ਹੁੰਦੀ ਹੈ, ਉਹ ਪੋਲਰਾਇਡ ਵਿੱਚੋਂ ਪਾਸ ਕਰਦੀਆਂ ਹਨ ਅਤੇ ਪਰਪੈਂਡੀਕੁਲਰ ਵਾਈਬ੍ਰੇਸ਼ਨਸ ਪੋਲਰਾਇਡ ਦੁਆਰਾ ਐਬਜ਼ੌਰਬ ਕਰ ਲਈਆਂ ਜਾਂਦੀਆਂ ਹਨ। An unpolarized light beam is equivalent to two equally intense beams whose planes of vibration are perpendicular to each other. When a beam of unpolarized light falls normally on a Polaroid, the vibrations of electric vector parallel to the transmission axis of the Polaroid passes through, while those perpendicular to the transmission axis does not pass through in the same direction. Therefore, the light beam that emerges out from the Polaroid has only half the intensity of the original unpolarized beam. This is how the unpolarized light gets polarized or plane polarized.
ਜੇ ਪੋਲਰਾਇਡ ਨੂੰ ਹੌਲੀ-ਹੌਲੀ ਪ੍ਰੋਪੇਗੇਸ਼ਨ ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਦੇ ਦੁਆਲੇ ਰੋਟੇਟ ਕੀਤਾ ਜਾਵੇ ਤਾਂ ਵੀ ਐਮਰਜੈਂਟ ਲਾਈਟ ਦੀ ਇੰਟੈਂਸਿਟੀ ਬਰਾਬਰ ਹੀ ਰਹਿੰਦੀ ਹੈ। ਇਸ ਤਰ੍ਹਾਂ ਪੋਲਰਾਇਡ ਤੋਂ ਨਿਕਲਦੀ ਲਾਈਟ ਦੀ ਇੰਟੈਂਸਿਟੀ ਵੀ ਬਰਾਬਰ ਹੀ ਰਹਿੰਦੀ ਹੈ, ਭਾਵੇਂ ਪੋਲਰਾਇਡ ਦੀ ਓਰੀਐਂਟੇਸ਼ਨ ਦੀ ਡਾਇਰੈਕਸ਼ਨ ਜੋ ਮਰਜ਼ੀ ਹੋਵੇ। ਲਾਈਟ ਨੂੰ ਪੋਲਰਾਈਜ਼ ਕਰਨ ਵਾਲੇ ਪੋਲਰਾਇਡ ਨੂੰ ਪੋਲਰਾਈਜ਼ਰ ਕਿਹਾ ਜਾਂਦਾ ਹੈ। ਉਹ ਇਸ ਕਰਕੇ ਕਿਉਂਕਿ ਇਹ ਅਨਪੋਲਰਾਈਜ਼ਡ ਲਾਈਟ ਤੋਂ ਪੋਲਰਾਈਜ਼ਡ ਲਾਈਟ ਪ੍ਰੋਡਿਊਸ ਕਰਦਾ ਹੈ। ਇਹ polarization ਹੈ।
In order to determine whether the light is polarized or not, we use two Polaroids. The first Polaroid polarizes the unpolarized light and is called the polarizer. The second Polaroid is called the analyzer, as it is used to determine whether the light is polarized or not. Let us now place the analyzer in such a way that its transmission axis is parallel to the transmission axis of the polarizer. We get polarized light from the second Polaroid. Now, analyzer is rotated so that its transmission axis becomes perpendicular to the transmission axis of polarizer. The polarized light stops entirely. The intensity of light emerging from the second Polaroid becomes 0.
However, the intensity of light emerging through an analyzer can be measured with the help of Malus law. According to Malus, when completely plane polarized light is incident on the analyzer, the intensity I of the light transmitted by the analyzer is directly proportional to the square of the cosine of angle between the transmission axis of the analyzer and the polarizer. If theta is the angle between plane of transmission of analyzer and polarizer, then I is proportional to cos square theta. If I0 is the intensity of polarized light incident on the analyzer, then I is equal to I0 cos square theta. It is clear that for theta equal to 0 degree or 180 degree, cos theta would be equal to plus or minus 1 and I would be equal to I0. It means when polarizer and analyzer are parallel to each other, the intensity of light transmitting from the analyzer is maximum. On the other hand, for theta equal to 90 degree, cos theta would be equal to 0 and I would also be equal to 0. It means when polarizer and analyzer are perpendicular to each other, the intensity of light transmitting from the analyzer is minimum. In general, we can polarize the light by reflection as well as by scattering. When a beam of white light is passed through a medium containing particles of sizes to the order of wavelength of light, then the beam gets scattered. When the scattered light is observed in a direction perpendicular to the direction of incidence, it is found to be plane polarized. This phenomenon is called polarization by scattering. In general, polarization by scattering is observed as light passes through the atmosphere. light reflected by shiny transparent materials is partly or fully polarized except when the light is perpendicular to the surface. Through this effect, polarization was first discovered in 1808 by the mathematician Malus. When unpolarized light is reflected from a plane surface such as air glass surface, the reflected ray is partially polarized. The degree to which the reflected ray is polarized depends upon the angle of incidence and the refractive index of the two media. However, the component of light beam that vibrates perpendicular to the surface is reflected less than the component vibrating parallel to the surface. It was British physicist Sir David Brewster who measured the angle of polarization by giving Brewster's law. According to this law, when unpolarized light is incident at polarizing angle IP on an interface separating air from a medium of refractive index mu, then the reflected light is completely polarized provided mu is equal to tangent of IP. This relation is known as Brewster's law. It has been observed that when light is incident at polarizing angle, the reflected component along and refracted component are mutually perpendicular to each other. In honor of Brewster, angle of polarization is also known as Brewster's angle. Let us have a look on its derivation. If the angle of incidence of the unpolarized light is 0 degree or 90 degree, the reflected ray remains unpolarized. But for angles of incidence between 0 degree and 90 degree, the reflected ray is partially polarized, but at a particular angle of incidence, the reflected ray is completely polarized. That particular angle of incidence is called angle of polarization. Since mu is equal to sin of IP upon sin R and according to Brewster's law, mu is equal to tangent of IP or sin of IP upon cos of IP. This shows that sin R is equal to cos IP or R plus IP is equal to 90 degree. This shows that the reflected ray and the refracted ray are at right angles to each other. With this, we come to the end of today's lesson. Let us summarize today's topic. In general, breaking up of light into different directions is referred as diffraction. Spreading of light waves that pass through a narrow opening or move past an obstacle is called diffraction. This effect is quite prominent if the size of the obstacle or opening is comparable to the wavelength of light. We know that the vibrations of the electric vector in an ordinary light takes place in all possible directions in a plane perpendicular to the propagation of light. If somehow vibrations of electric vector are confined to only a single direction in a plane perpendicular to the direction of propagation of light, then it is called plane polarized light and the phenomenon is called polarization. However, the angle of polarization can be measured by Brewster's law. According to this law, when unpolarized light is incident at polarizing angle IP on an interface separating air from a medium of refractive index mu, then the reflected light is completely polarized provided mu is equal to tangent of IP. I hope you have all understood the phenomena of diffraction and polarization. Before the end of this class, let me ask you a few questions. My first question is, define diffraction. The definition is spreading of light waves that pass through a narrow opening or move past an obstacle is called diffraction. Another question is, what are the different methods for polarization of light? The answer to this is, common methods of polarization of light are polarization by scattering and polarization by reflection. The next question is, define Malus law. The answer is, according to Malus, when completely plane polarized light is incident on the analyzer, the intensity I of the light transmitted by the analyzer is directly proportional to the square of the cosine of angle between the transmission axis of the analyzer and the polarizer. Students, ਮੈਨੂੰ ਉਮੀਦ ਹੈ ਕਿ ਤੁਹਾਨੂੰ ਅੱਜ ਦਾ ਪਾਠ ਕਾਫੀ ਦਿਲਚਸਪ ਲੱਗਿਆ ਹੋਵੇਗਾ। ਅਗਲੀ ਵਾਰ ਇੱਕ ਹੋਰ ਨਵੇਂ ਵਿਸ਼ੇ ਨਾਲ ਫਿਰ ਮਿਲਾਂਗੇ। Thank you for your attention and see you next time again.